Today, we're just going to talk about equipment and instruments for refrigerant handling and service. This is what we're going to be utilizing on a day-to-day basis. You know, we're hooking things up, putting in equipment, and we need to be able to safely handle refrigerant. We need to do so because not only is it good for the environment, like we talked about, it's going to keep us safe, and we're going to minimize waste of refrigerant, that sort of thing. So we're going to identify and explain the use of the various types of refrigerant cylinders, which are critical for refrigerant handling, disposal, that sort of thing. Differentiate between the various types of pressure gauges, compare various types of service valves and their positions, explain the purpose, construction, and operation of a gauge manifold, and identify the various types of leak detection equipment and explain the appropriate use of each. All right. Some of this stuff we've already covered in our previous chapters, but the book is going to go a little bit more into detail, make sure that we're covering all of our bases here. Okay. So we're going to talk about vacuum pumps and how to change its oil, why do we want to change its oil, and identify and demonstrate the use of various recovery machines. All right. So we've got refrigerant cylinders. All right. They're used to store the refrigerant inside them. We have to transport refrigerant from one place to another, and we're going to use these cylinders to do just that. All right. If we were to just take that refrigerant, expose it to the atmosphere, well, it's just going to disappear. All right. We've got storage cylinders, we have disposable cylinders, we have recovery cylinders. All right. Each one has its own purpose. All right. We have pressure release protective devices on all these cylinders. They're there to protect these cylinders from rupturing. All right. We're talking about high pressures. Once those high pressures start to expand, it starts putting outward pressure on the cylinder. Eventually, the pressure can get so great that something's eventually going to give. And rather than having a bomb, we're going to put in a safety device. That safety device is going to release some of that pressure so the container doesn't rupture. All right, so we've got the spring-operated relief valve, a rupture disc, and a fusible plug. So, fusible plug, rupture disc, spring-operated relief valve, they're all shown here. Basically, the fusible plug is just going to melt once it reaches a certain temperature. So we left our tank in our van. It's a really hot day. Let's just say it's Arizona. And now all of a sudden we're approaching 130, 140, 150 degrees inside of our vehicle. Well, this plug is going to eventually melt. It's going to release the refrigerant so we don't have excessive pressure. All right. We can also have a little disc inside here. That disc is just going to burst once it reaches a certain pressure. Or we've got a mechanical device. Basically, there's a little spring in here, and once the pressure reaches a certain amount, that spring is going to give, and the pressure is going to relieve. You're actually going to see this spring-operated relief valve a lot in our industry. All right, you're going to find it not only on tanks, but you're also going to find it on water heaters. That's a really common place you're going to find that. We don't want that water getting too hot inside of a water tank. If it does, hopefully you guys have seen this, Mythbusters, that water tank can act like a missile. It's going to shoot on out through your house and nothing's going to get in its way. So we put on a pressure relief valve, all right, and a temperature relief valve. It's a combination. Those both go on the water heater. We have a boiler system. Boiler system is going to have something very similar, all right, different pressures, different temperatures. But either way, we're going to try to maintain some type of safety device on there to ensure that we don't have any type of explosion. All right, cylinders, they're regulated by the DOT. They have to meet certain specifications for them for you to be able to transport refrigerant. So what that means is our recovery cylinders, all right, we talked about them a little bit. We'll talk about them a little bit more in this chapter, but they're gray and yellow. And what ends up happening is those cylinders have to meet Department of Transportation specifications. All right, we're moving cylinders back and forth. We're refrigerant. We need to transport them somehow. If we get into an accident or something, we want to make sure that they don't rupture on us. Okay, they don't meet the same protocols for disposable cylinders. Those are completely different. Those are the ones that we grab to fill our systems with. The pink ones, the green ones, whatever they are. Those don't meet the same criteria, but just so you understand, everything is regulated. All right. Cylinders with the corrosive refrigerants need to be certified every 5 years, and then cylinders with non-corrosive refrigerants every 10 years. So what will end up happening is, if you get a tank, a recovery tank, you're going to take that recovery tank, you're going to fill it up full of refrigerant. You don't want to mix the refrigerants in a recovery tank, all right? You're going to keep it separate. So if we're working on R22, we're going to have one recovery tank. If we're working on 410A, we'll have another recovery tank. Once our tanks are full, we need to dispose of them, all right? We can go over to one of our supply houses or distributors, something like that. Sometimes you have to pay a fee to dispose of it. You hand them the tank, they hand you another tank, you're good to go. You don't have to recertify those tanks because you're just swapping tanks. If it were your own tank and you didn't swap it out, you just sort of transport it into another tank, well, guess what? That tank of yours would have to be recertified, all right? We want to make sure that there's no rust or anything else on the inside, and it meets certain specifications so it doesn't fail or potentially rupture. Storage cylinders come in 100 and 150 pounds, and they're used to charge refillable cylinders in the shop. All right, so basically we're just going to use this to, just a means of transporting large amounts of refrigerant. Instead of having tons of little tanks, we're just going to have one big tank, and it's going to do the job of many. All right, it's fitted with a valve and a cap. These are actually really important. If you're ever moving this guy around, make sure the cap is on. The reason being is we have a valve at the top. If that shears off, this turns into a missile. All right, that cap should always be on when this thing is being transported. If it's being transported, use a dolly. Make sure the tank is strapped to the dolly, so forth. We're going to take as many precautions as possible to ensure that this thing doesn't tip over. One of our previous videos, I showed you, some guy sledgehammering the top off, and it just shot hundreds of feet into the air. So imagine, if that were in the back of your van. All right. All right. Use a hand truck, secure the cylinder. Just talked about that. Disposable cylinders. All right. They're designed for a one usage only. So whatever refrigerant's in there, as soon as we utilize all that refrigerant, that's it. They're done. They're no more. We're not going to fill them back up. Okay. They're not meant to be reused. All right. We don't want to put in any type of used refrigerant in there or anything like that. They have a thin wall compared to a recovery cylinder, so the walls may eat away, so forth. We may put too much refrigerant in there, so we don't want to do that. Okay. The advantages: they're easy to handle, and then they eliminate the need to refill. All right. So disposable cylinders. This is what everybody's going to be pretty much using. All right, before disposing or recycling, recover all refrigerant into an approved recovery cylinder. All right, there is going to be some leakage. We can't help it. We're purging our lines. We're putting our hoses on. Some refrigerant's leaking by. It's going to happen. Okay, there's nothing we can do, but we're going to try to at least recover as much of that refrigerant into our tanks as possible. We're going to evacuate the cylinder down to atmospheric pressure. Okay, so basically what that means is we're going to suck out as much of that refrigerant out of that disposable cylinder as possible. All right, we're going to try to get every little last drop out of it. Okay. Many refrigerant supply stores offer recycling. Absolutely. You just need to go to a supply house, talk to them, see how they handle their refrigerant disposal, and you can go from there. It's illegal to transport recovered refrigerant in a disposable cylinder. Absolutely. All right, if you got a disposable cylinder, don't try to fill it. All right, there may be certain issues that may come in contact, or certain issues that you're going to have. One being, let's just say you recovered some 410A and you put it into an R22 cylinder. Well, somebody's going to grab that 22 cylinder thinking it's 22, not 410A, and you're going to fill up that system with the wrong refrigerant. Another thing, you don't know what was in the system that you just recovered. There could have been dye, there could have been acid. and now all of a sudden you're reintroducing that into the system you're trying to repair. So don't do it. All right, we just talked about it. Illegal to transport recovered refrigerant. Do not use disposable. And here we have a recovery cylinder. All right, like I talked about, we've got a gray body with a yellow top. Really easy to identify. They're designed for storing recovered refrigerant. So if we're going to be pulling out R22, I'm going to have one recovery tank. If I'm pulling out 410A, I'm going to have another. Depending on however many refrigerants I have is going to determine the amount of recovery tanks I have. All right. The valves, the gas is usually blue, liquid line is usually red, and then you can read the valve handles to identify the valves. So if you look at the handles very closely, you're going to see that they're going to say vapor, liquid, whatever the case may be. Off to the right here is our little burst disc or fusible plug. Okay, little safety devices on there. Pressure gauges, they're going to help us know how our system's operating, whether we're low on charge, too high, other issues are really happening. All right, we're going to use the gauges to help us identify the system. All right? We're going to measure pressure of a fluid in a container, or I should say gauges help measure pressure of fluid in a container. They also provide information about inside of refrigeration system. All right, you have a board-on tube, which is the operating element. A lot of times, everybody's going to be really known to digital gauges. When you first start out, you guys may have some already, and you're going to go with the analog, so you eliminate that board-on tube. But digital is sort of the future, all right? The gauges are also going to help you read vacuum, tell you your high pressure, tell you your low pressure, all right, that sort of thing. We've got a vacuum gauge. Vacuum gauge is going to be used when we're evacuating our system. We want to make sure that we have no bad things in our system. All right, those bad things are non-condensables. We want to make sure that all of the air, moisture that's in there that may affect our system from operating properly are removed. Okay, I know we talked about this before. Using compound gauge. Compound gauge is limited. It's going to max out at 29 inches of mercury. Well, what the heck does that mean? I don't know, but there's roughly 760,000 microns in an inch of mercury. So we want to, in 29 inches of mercury. So what we want to do is we want to ensure that we're evacuating the system as close to possible to achieve a absolute vacuum, and the only way to really do that is to use a micron gauge. It's just a finite measurement to tell you exactly what's going on. Okay. Needless to say, if we are evacuating, we want to generally hit about 500 microns. That's usually what a lot of manufacturers are recommending. Some people have different ways of doing it, but I know, for example, like an American Standard, they're going to want you to pull down to 250 microns. Let it sit for a minute and see what ends up happening. Mitsubishi, I think they want you to pull 500 microns and let it sit for like 30 minutes and see if there's any rise. So just read the manufacturer's recommendation and go from there. All right, compound gauge, it's going to tell you your pressure, all right, on the low side. Also going to tell you the saturation, temperature pressure relationship between different refrigerants. So this one, for example, is a 422A, and then we have 417A, and then we have 422D. All right, so those different pressure temperature relationships are available on the compound gauge for those refrigerants. If you didn't have, if you're testing a different refrigerant, you would just have to use a PT chart, but the pressures are still going to be the same. We also have the vacuum, at the bottom. The needle would go in reverse, and it would tell you how many inches of mercury we have. High pressure gauge, we put this on the high side, and it's going to read our pressures for our system. Yet again, different refrigerants, with their pressure temperature relationship. A lot of the new refrigerants, they're going to start reading a little bit higher than 500 psi. 410A, usually about a 600 psi, is where you're going to see your gauges start to max out at, and that's only for testing purposes. A lot of times there'll be a high pressure cutout switch, and that'll probably engage right around that 500 pressure mark or psi mark, so you don't have to worry about it. But you want to ensure that your gauges read right around like 600 psi, I'd say. Okay. Carrier calibration. I don't know of many analog gauges that you can really calibrate anymore. Digital, there's a zeroing setting. You may be able to use some inert gas, that sort of thing, depending on the manufacturer, to zero them out. But we just have to know, where we're at as far as sea level elevation goes, to know where our gauges should read. Because if we're at sea level, we're going to read 14.7 psi atmospheric, as opposed to being up in Denver, we're going to read 12.2, all right, psi atmospheric. Reason being, we've got less gas pushing down on us, we're higher up, less gravity, that sort of thing, and that does make a difference. So if you're going to be in Denver, you have to understand that there's almost a 2.5 psi difference between sea level and where you're at. Luckily here in Chicago, the sea level isn't high enough, so we just go off of 14.7. Service valves. All right, they provide access to the system, they ensure continued smooth operation, and they control access to the service port. Basically what we're going to do as technicians, we're going to take our hoses and we're going to attach our hoses right here to the Schrader valve. Okay, what ends up happening is there's a little depressor inside our hoses. It's going to push down on this little point right here, and that's going to cause the Schrader valve to depress, which in turn allows refrigerant to come out. That refrigerant coming out is going to be read by our gauges. All right. These service valves, just so you guys know, they are a point of leakage. Okay. If I go ahead and I put my hoses on and I walk away, sometimes the Schrader valve never reseats. Okay. And what ends up happening is I get refrigerant that starts to leak out. So I check the system, everything's good. I come back, all of a sudden I get a call the next day. Hey, my system's not running. You go out there, it's bone dry. Why? The Schrader valve got stuck and it never reseated and leaked out all the refrigerant. So if it's a system that hasn't been serviced in a while and you're working on it, it may be good just to replace that Schrader valve. Okay. I think we'll cover that a little bit too. Another place for leakage is the valve stem right here. All right, what I can do is I can actually isolate the system. I can take this cap off. There's going to be a little hex head inside there. I put my Allen key in there or my service wrench. I can tighten, I can loosen little valve down, and what's going to end up happening is I'm going to separate one side and the other. I do this both to the high side and the low side, and now all of a sudden I can work on my system, do what I need to, whatever the case may be. All right. We also have the king valve here. What ends up happening is there's different operations of the refrigerant being able to flow through. So ideally what ends up happening is we would have our refrigerant coming up over and flowing through our Schrader core. All right. There actually is no Schrader core in a king valve. All it is just an opening. So if you do go and you notice that, hey, I don't have a Schrader core or I'm not getting any pressure, well, you may be working on a king valve. And the way they operate is I've got a plunger or like a seat with a stem. And what ends up happening is as I back this guy out or back it in, it's going to move up and down, which is either going to allow refrigerant to flow through the system, or it's going to allow refrigerant to flow up over and out through where your service ports would be, where you connect your gauges. So if this thing is all the way back front seated, we're not going to allow refrigerant to go through the system. We're going to allow it to go through our hoses or out the service port. Vice versa, if we're back seated, we have no refrigerant coming out. I've had refrigerant actually leak out on me because this thing was back seated, but it still wasn't good enough. The refrigerant's still leaking by, and that's when it almost shot and hit me in the eye. So I had like a little liquid refrigerant waterfall streaming out of the system. All right, mid position, cracked open. Basically, we're allowing refrigerant to go through to the system, and we're going to get a reading on our gauges. All right, always use fixed wrench when cracking open stuck valve. Valves can be quickly closed again if a leak or breakage occurs. All right, all you need to open this guy just a tad bit, just so that the refrigerant flows through and we can get a reading. All right, we don't have to open this thing all the way up. If we open it all the way up, we may end up front seating it, and we're going to get no refrigerant going through. All right, so we have the low side valves, we have high side valves. Okay, basically they're just going to be on both sides of the system. The reason they come on both sides of the system is the units are pre-charged with refrigerant from the manufacturer. If you open up the valve after you make all your connections, you're going to allow that refrigerant to travel through and get into the system. That's where we as technicians have to come in and adjust the charge. Generally, the manufacturer is only going to give you about 15 feet worth of refrigerant. All right, so if I've got 15 feet of line set, that's perfect. If I have more, well, I'm going to have to add refrigerant. If I have less, well, I may have to pull some out. So if I need to work on the system, another trick I can do is I can actually close off the high side valve. I can turn on the compressor manually. I'm going to pump all the refrigerant into the condenser. It's going to start to accumulate in there. Once I basically fill up that condenser, I'm just going to go ahead. I'm going to close off the low side service valve, and that's going to trip a majority of the refrigerant in the condenser. The rest I recover, and I can work on the system. That way I don't have to pull out all the refrigerant out of the system. All right, service valve maintenance and operation. Clean and oil valve stems before turning. Sometimes they do get stuck, so we want to make sure that there's no gunk on there or anything like that, because that stem is going in and out of that valve body. All right, reduce rusting by coating valve body with refrigeration lubricant. You want to use some lubricant on there if we have it available. I mean, worst case, WD-40, something like that. Just spray it on there, make sure that it it's coated. All right, you want to match the wrench size to the valve stem. Okay, we don't want to use anything too big. Don't use channel locks if you have them. The reason being, you could potentially strip it, not char, but you can almost round out the nut, if you're not using the proper tool, and so then all of a sudden it becomes more difficult to gain access to. All right, there's a packing nut too. That packing nut is there. Let's see. This one doesn't show it, but there is sometimes a little nut on the service valve that we have to tighten to make sure that we're not getting a refrigerant leak out of there. All right, and oil threads of the service port. So this is just a image of a Schrader valve. All right, what ends up happening is this little guy screws into that body. All right, we've got this little depressor right here. As we depress downwards, this guy opens up and it allows refrigerant to travel through. We also have piercing valves. Piercing valves are a little bit tricky. All right, what they have is they've got a little bit of a needle inside here, and what you end up doing is you mount this onto a piece of copper. All right, liquid line, vapor line, whatever you want. And what you end up doing is you slowly tighten this stem down. As you start to tighten it down, there's a little needle, and that needle punctures through the refrigerant line, and now all of a sudden you're able to see what your charge is. All right. Sometimes there's systems that are completely sealed; they don't have access ports on them. We're talking about like refrigerators, water coolers, window units, those sort of things. They're just charged from the factory, and we want to be able to work on them. Sometimes we can't. So what we need to do is we need to gain access. So we use this bolt-on piercing valve, make that hole, pull out our refrigerant, do our repairs, and then we could recharge the system. These will leak on you, so if you're going to do a permanent repair, something that you're going to use or you want to maintain, you should braze on a service port to that line that you just punctured. All right, this will leak, so we're trying to minimize that as much as possible, so that way if we have something that's braced on, we can still access the refrigerant charge without having a potential leak. All right, brazed on piercing valves, they're good when there is good access to area of straight tubing. All right, so we want to put it on a piece that's straight. We don't want to put it onto a bend or 90 or anything like that. Before installing, we want to evacuate the refrigerant. Yep, we'll use the piercing valve. All right, we're going to use the bolt-on type, remove all the refrigerant, and then we can braze on our own service port at that point. All right, so our gauge manifold, it's got the compound gauge on there. It's got the high pressure gauge, and it's got a minimum of 3 ports, minimum of 2 valves. All right, so we've got these little handles on here, and what these handles do is they allow me to flow refrigerant through my hoses. All right, I think the next slide shows us that. All right, what do we use our gauges for? We're going to check the pressure of low and high sides at the same time. We're going to add or recover refrigerant. We're going to add oil, and we're going to bypass the compressor. Okay. Purging gauges, that's important. All right, we want to make sure that we remove all the vapor, dirt, or moisture that's in our hoses. All right, so what we're going to do is we're going to allow a little bit of refrigerant to flow through our gauges. Let me go back here. There's a couple of ways of doing it. One way is we've got this little area right here that threads on to the manifold, and so when we take our hoses and we connect them to the unit, that refrigerant is going to come through that hose. It's going to come upwards, and if we leave this open just a slight bit, we're going to get all that junk that's in our hoses to be pushed out through the top, and then we quickly tighten this, and now we know that we've got pure refrigerant inside there, and we don't have any dirt, anything like that inside. The other thing too is, especially on the low side, if I did have any dirt or air inside my hoses, I'm not going to get that stuff get sucked back into the system. All right, so that's what we do with purging. We can use virgin refrigerant tanks to do that too, especially if you have like ball valves on the end of our hoses. We can do it that way. All right, purging releases content into the atmosphere. It's okay to do little bits of purging, but we're not going to just purge our refrigerant tanks into the air. All right, hoses are acceptable. We always use quick connect fittings to release as little refrigerant as possible. So that means either we have ball valves or we have hoses that are just going to trap the refrigerant inside. Okay. EPA allows technicians to release small amounts of refrigerants during recovery, repair, purging, and charging. Okay. So this is basically how our gauges work. Okay. So we've got a just a 2-port gauge right here, and basically what we have is we've got our low side and we've got our high side. What ends up happening is as soon as we hook up our gauges, I'm going to get a pressure reading on my low side. I don't have to do anything with the valve right here whatsoever. it's going to give me a reading. As soon as I hook up my high side, it's going to give me a reading. All right, we're getting a reading while the system's running. While the system's not operating, we're still going to get a reading, but that reading is going to be equalized because I don't have any pressure differential between the low side and the high side. All right, that refrigerant just equalizes. But as that compressor runs, this is something more accurate. All right, you're going to get the needle pointing in one direction, you can get this needle pointing in another, and it's going to tell you exactly what's going on. Now all of a sudden, we're evacuating system. Okay, we're pulling all the refrigerant out. All right, how do we do that? Well, we're going to connect this third hose to our vacuum pump, or we're going to connect it to our recovery machine in this case. The recovery machine is going to suck out all the refrigerant. We're going to open our valves. All right, previous slide, they were closed. We have no refrigerant flowing through our hose, right? And we can, as soon as we open up one side, it's going to go right into the yellow hose. If we open up the other side, it's going to go into the yellow hose. You open up both, now all of a sudden they're all going into the yellow hose. It says vacuum pump right here. I would never hook up my manifolds to a vacuum pump. The reason being is it's another point of failure. Meaning, if my hoses aren't connected correctly on the low side, I may get a little bit of air that keeps getting sucked in, gets sucked in, and I'm never going to get a proper evacuation of the system. So, to properly evacuate, all I need is a micron gauge and my vacuum pump, and I want to use an actual dedicated evacuation hose. All right, Appion makes one. There's another company, I think AccuTools has another one, like the True Blue hose. You want to use something that's dedicated for recovery. If you try doing an evacuation with your charging hose is not designed for that, so you're actually going to start to pull in molecules through that hose, and you're never going to achieve a proper micron level. All right. So if we're charging via vapor, we're going to have our yellow hose connected to our disposable cylinder. We're going to let the system run, and we're going to control the amount of refrigerant going into our system via the valve. So we're going to slowly open up the valve. We're going to let some refrigerant come in, get sucked in, go into our system, and we're going to keep charging it until we obtain the proper superheat or subcooling. If we need a liquid charge, we can do the same, except we're going to charge on the liquid side. All right, we're going to open up the liquid valve. We're going to go, through the yellow hose into the red hose into our high side. Now, I don't recommend charging at all on the liquid side when the system is running. All right, the pressures are going to just be too great, and your tank is going to have a hard time overcoming those pressures. All right, remember, our pressures are trying to equalize, and so whatever pressure is greater is where our refrigerant is going to go. So if my high side is 400 psi, but my tank is only 200, well, guess what? I can open up this valve as much as I want, but the refrigerant is going to come backwards. It's going to go through my red hose, through the yellow hose, into my charging cylinder, and that's not what we want. So if you're going to do this, make sure that the system is off. Generally, we do this when the system is new. We'll allow liquid refrigerant to go in on both sides, let the system equalize, get enough refrigerant in there, start the system up, and then slowly charge on the low side. Refrigeration system analyzer. Basically, this is just a fancy way of saying that this is a digital gauge. Digital gauges are really nice because it comes with your temperature probes right there. You basically put them on the liquid suction line, take your hoses, hook them up. It's going to tell you all the information that you need about the system. What's going on, what's my saturation temperature, what's my subcooling, my superheat. It's going to calculate all that stuff for you. You don't have to do a single solitary thing. So those are really cool, nice to have. That's what I definitely rock. Nice cool thing too is a lot of gauges, they're actually becoming Bluetooth capable, and so now all of a sudden, instead of having this big guy to carry around, you just have a couple of probes, you hook them up, you look on your phone, it's going to tell you exactly what's going on. And then with that setup, you can actually hook up multiple things. So I can hook up a temperature sensors, a hygrometer. We can do static pressure, which you guys will cover later on, but that's basically, let's just call it your blood pressure of your HVAC system for your ductwork. Do all this stuff at your fingertips, and then you can really dial in the system like it's supposed to be. So then we have leak detection. All right, so we've gotten to the point where, hey, our system's leaking. We need to be able to fix it. All right. A lot of times, guys will come in and they will just give you, the lowdown, like, oh, hey, your system's leaking. It's low on charge. We're just going to fill it up and we're going to call it a day. You can do that, but I advise against it. The reason being, you show up on site, you haven't been there before, you don't know what happened. So yes, we're going to have to put some charge into that system. We know it's low. We hooked up our gauges, but inform the customer. Let them know there is a leak. I'm going to put refrigerant in there. I don't know how big the leak is. This may last a week. This may last a month. It may last a day. I don't know. So we're going to try to see what's going on. Sometimes what happens is when technicians come in and they hook up their gauges, year after year, they're hooking up their gauges and they're pulling out 6 foot worth of refrigerant, all right, both low side and high side, and they're doing this for years. Eventually it's going to get to the point where, hey, my system's low on charge, it's not operating, but I've been maintaining it every year, right? Technicians are coming out doing their job. Well, they've basically just taken all the refrigerant out of the system and your system's not operating. All right, so that's why there's a new thought process of being non-invasive, not hooking up your gauges unless you really have to. But we know that we have a leak, all right? How do we find this leak? All right, there's a couple of methods of doing that. All right, we have bubble solutions. Bubble solutions, just like a little soapy bubble, you just spray it onto your joint. You would spray it onto wherever we have braze fittings at. We're going to spray it on there and we're going to look for leaks. This sight glass can actually be a really big spot for looking for leaks. We can spray it all down, and with the pressure escaping, we're going to get a little bit of a leak. All right, we may get some bubbles showing up. We also have fluorescent dyes. Fluorescent dyes do take some time to operate. All right, you can't just put it into a system, expect it to work immediately. It's got to operate for quite some time, maybe a day, maybe 2 weeks, maybe 3, who knows, depending on the size of the leak. But once it's in there, you take a UV light or a special light and you basically start scanning and you start looking for anywhere along the copper where that refrigerant leak will actually show. Okay. Halide torches, that was old school. You basically walked around with an open flame and you would look for any refrigerant leaks, and if you found one, that refrigerant or the flame would actually change color, because now all of a sudden you're starting to burn a flame, or you're starting to burn refrigerant with that flame. Another way is electronic detectors. So basically they're just like little audible machines that are going to give you a beeping, and as you start to get closer, they're going to start to beep faster until you basically find that leak. All right, think of a metal detector of sorts. So tips for detecting leaks: check connections early in your search. All right, I'll be honest with you, the easiest places to go and check for leaks: check your Schrader cores. You're going to check your valve caps. Valve caps are notorious for leaking. All right, that's where we put our service wrench to. We talked about it last week a little bit, was using Nylog, on that service valve. That was a great place to apply a little bit of that sealant on there, just to make sure that if we are leaking from there, it buys the customer a little bit of time. We can't really fix it, we can't pull it apart. It's just a matter of cutting it out and putting in a new one if that's the route they want to go. At that point, it's usually time for a new system anyways. All right. A big indicator that you have a leak is oily or dusty areas. All right. If we have a leak, we have oil that's traveling through the refrigerant. All right. That oil is going to escape as well. And so now all of a sudden we may have a very oily area. If that's the case, that's a good indicator we got a leak, and I'd start looking right there. You can block off search area to eliminate wind or breezes. All right, block bright lights when using color changing methods. Sometimes that's difficult to do, but you do the best you can. If you're on a rooftop and it's a really sunny day, bring a piece of cardboard, bring something just so you can isolate the sun away from that area as much as possible. Turn off nearby equipment when using ultrasonic detector. You want that ultrasonic detector to pick up your leak. You don't want it to pick up anything else running in the background. And then operate the system to build up pressure. So the system's got to be operating so that way there's enough pressure in there, so that way we can try to find that leak a little bit better. Another cool tool that I just found out about today, FLIR makes it, and it's basically a refrigerant leak detection camera. So it's like a thermal imaging camera that would basically find your leak for you. I don't know much about it, I just saw it today, but that's another way of going about and looking for stuff. So Section 608 of the Clean Air Act states leak repairs are required within 30 days if a leaking system contains 50 pounds of refrigerant. All right, if the system has yearly leak rates at or above trigger levels. Your trigger level is 35% for commercial and industrial systems. Trigger level is 15% for comfort, cooling, and other applications. All right, so what does that really mean? We basically have to fix our systems, okay? We can't just let them, leak out into the atmosphere willy-nilly, all right? We want to make sure that no more than 15% leakage on a residential application. So what that means is if I have a system that is, we'll just say, simple terms, 10 pounds, all right, I wouldn't want it to leak any more than 1.5 pounds, per year. All right, if I leaked 1.5 pounds every year, well, then I need to fix that. Otherwise, it's acceptable for it to just leak out. If it's 1.4 pounds a year, well, great. Just keep leaking out and you can just put new refrigerant in. Otherwise, you have to make the repair. You have to find out where it's leaking from. All right. Keep accurate logs of customers' refrigerant use and loss, which will help technicians detect leaks early. That's important because you want to know what the previous tech did. All right. How much did you put in? Well, what did you do? How much? Where? How? Anything in between. Did you fix a leak? Did you put in dye? That all helps in the future. You determine this year, hey, you had a leak, we put in half a pound. The next year you come in, hey, we've got a two pound leak. All right, what's going on? Customer may want to invest in a new piece of equipment instead of trying to find this leak. All right. Sometimes you're going to get micro leaks. All right, micro leaks develop in the evaporator. Things break down. The metal just starts to deteriorate over some time, and you'll have a leak and you won't be able to find it. All right, and you won't be able to do the repair. It happens, so finding leaks can be very difficult and very time consuming. All right. The earlier a leak is detected and repaired, the smaller the environmental impact of that leak. So bubbles, soap and water or a patented solution, they're either brushed over the top or they're sprayed. All right, the vapor causes bubbles to form. The advantages: low cost, easy method of leak detection. It's the most reliable test in presence of urethane. Disadvantages: larger leaks may blow through without bubbling. At that point, you would probably know that you've got a leak, right? Soap bubbles are really great. If you do have a very minute leak, micro leak, it may not detect it though. So, okay. This is what a leak does look like. All right, we've got little tiny bubbles, happening. They're bubbling up, so we know that this is a very small leak. This is on the side of an evaporator. or hey, we've got this really big bubble, starting to form. Okay, um, the pressure's trying to escape, and it's going to go through that bubble solution, which is going to cause, this to appear. Dye-based leak detection. All right, it's injected into a system. System returned to normal operation, and it's visually inspected for dye at various points. It can work. It's just a matter of when and if. It may take some time before you were able to find the leak. All right, especially on larger systems, that sort of thing. Halide torch we talked about. When halogen refrigerant contacts flame, the flame becomes light green. All right, works with all halogenated refrigerants. Yeah, nobody really does a halide torch anymore. There's better stuff out there. Plus, we don't want to be breathing in any of the combustibles from that chemical reaction. So we're just going to go ahead and skip the whole halide thing. Electronic leak detectors. This is probably more prevalent. Basically, you're just going to take the sensing tip. You're going to run it around, the fittings. You're going to make sure that it's running like it's supposed to, or no, sorry, it's operating like it's supposed to, and you're not going to get any type of indicator. All right, there's usually an audible and a visual alarm indicating whether you found the leak or not. And then as I start to get closer to the leak, I can adjust the sensitivity so that way, once I really get to the point, it's going to go crazy, as opposed to me just putting in the area that's full of refrigerant. Do not use halide. Yeah, who cares about halide torches? So we also have the ultrasonic. All right, ultrasonic is going to go based off of sound. That's why we want to make sure that we have a quiet area, and it's going to work off the principle of detecting the sound a vapor makes as it leaves a pressurized system. All right, really good stuff. I've never had the pleasure of using it, but I do know a lot of people that do swear by them. So a couple of different ways of looking for leaks here. Vacuum pumps. Vacuum pumps are going to be used to pull vacuum for our system. All right, we can't just use the compressor to do that. We want to make sure that we're removing all the non-condensables, all the bad stuff out of there. All right, so we're going to use this machine. It's used to create a vacuum for evacuating system before charging. Basically, every vacuum is going to be a little bit different, but they all work off the same principle. There's a motor in the back. It's going to spin some vanes. The vanes are going to create suction, and it's basically going to pull out all the stuff out of the system. It's going to use oil in there to keep those vanes nice and lubricated, and the oil is going to trap any of the moisture that was inside the system. So what that means is after so much time, you need to change the oil in your vacuum pump. If you do not change the oil in your vacuum pump, then you won't be able to achieve a proper evacuation of your system. So just a couple of tidbits there. You're pulling a system, all of a sudden you can only pull down to 1,000 microns. Maybe it's time to change your oil. Simplest thing to do is normally we take our micron gauge and we connect it to the service port of our system, but for testing our vacuum pump, we can connect it directly to our vacuum pump, and then the vacuum pump should pull down to about 50 microns. If it doesn't pull to 50 microns or greater, well then we've got a problem with our vacuum pump. So we've got a couple of different types. We've got a single stage pump, and then we've got two-stage pump. All right. The single stage pump is used in a triple evacuation method. All right, so triple evacuation, how that operates is we're going to, we just did a leak test on our system. All right, we filled up our system to 150 psi. We're going to start to remove that nitrogen from our system. All right, we're only using nitrogen for that test. Before we remove all the nitrogen out of our system, we're going to leave it at maybe like 5 psi. We're going to hook up our vacuum pump. We're going to start to pull out our nitrogen. We're going to start to pull a vacuum. We're going to eventually get to the point maybe 2,000 microns. We're going to stop. We're going to fill the system up with nitrogen. We're not going to allow any atmospheric air to get into the system. We're going to fill it back up until the pressure reads 0 because we were at a vacuum. We'll then turn on the pump. We'll evacuate again till we reach 1,000. We'll go ahead, fill it up again with nitrogen, repeat the process, and then the third time we'll be able to pull our vacuum down to the desired level. The reason we do this is because we're going to push out all the contaminants through the system. All right. Some people will say that nitrogen, and air or oxygen and moisture absorb and blah blah blah. That's not true. All we're really doing is using the inert gas of nitrogen, and we're going to just push it all throughout the tubing to make sure that nothing really resides in there. Okay. Two-stage pumps. They're used in the deep vacuum method. You can use a single-stage pump if you want to pull a deep vacuum. It just may take you a little bit longer. The two stages work in unison to allow you to just turn on the system and run and pull a vacuum straight to 500 microns. Purpose of the oil: lubricate the pump, provides fluid seal for the air gases. Yep. We got to replace that oil frequently. Check the sight glass for oil level and quality. Once you start to see that oil turn to a milky color, it's time to change it. Okay. A lot of manufacturers, they're actually going to tell you that you want to change that oil regularly, pretty much between every evacuation. That's up to you. I mean, if I did a pretty clean system, a new install, then I may be able to get a few systems out of that oil. But if I did a really nasty one, or it took me a long time, that sort of thing, I'd probably want to change that oil. So some units even come with their own oil canister. Others require you to open a plug and drain the oil. Refrigerant recovery is the process of removing refrigerant from a system and storing it in an external container. So I can't use a vacuum pump for that. I have to use a specialized piece of machinery. Why? Because I'm going to be dealing with not only liquid refrigerant, but I'm also going to be dealing with vapor. And so my vacuum pump isn't designed for that, but these recovery machines are. All right. They're going to pull out all that stuff, put it into your recovery tank, and we're going to call it a day. Section 608 of the Clean Air Act requires refrigerant to be recovered and recycled. All right. We're going to take that recovery tank, we're going to drop it off to our distributor. They're going to give us a new tank. Day's over, we can go on and keep making our money. Recovery equipment must be certified by an EPA-approved testing organization. Basically, when you buy your recovery machine, it's going to have a sticker or label on there stating that it is okay to remove the refrigerants that you're going to be working on. All right. I know we talked about it last week a little bit, talking about some of those flammable refrigerants. The recovery equipment that we have now won't be able to handle those refrigerants. So we need to make sure that we use the proper recovery machine for the refrigerants that we're going to be working on. I still think we're a few years away from that, but just keep that in the back of your head. You may need new equipment. All right. Refrigerant cycling is the process of cleaning refrigerant for reuse. All right, separates out the oil and it passes through filter dryers. Basically, what this is just a refrigeration cart. This is what you're going to see in the automotive sector. We're not going to really use it so much. I mean, if you start working on cars, then yeah, you may need this, but otherwise, no. We're just going to be recovering our refrigerant, and we're going to be putting in virgin stuff. All right. If we recover it, we can put it back into a homeowner's unit. Otherwise, we have to dispose of it properly. Refrigerant reclaiming. It's the reprocessing recovered refrigerant to be chemically pure. So we're making sure that there's no types of nasties in there, making sure that it can be reused. Again, it's almost as if it was just made fresh from the factory. All right. It must meet certain AHRI standards. Okay. Reclaimed refrigerant use can be charged back into any unit designed for use with that refrigerant. So if I pull out a 410A, well, guess what? It can go back into another 410A system. An environmentally conscious technician not only minimizes and repairs all refrigerant leaks, but also takes steps to ensure that refrigerants remain pure, clean, and dry. So if you were to use dye, for example, your leak testing, unfortunately that system is now contaminated and you won't be able to use that refrigerant again. So if I put that refrigerant into a recovery cylinder, all that refrigerant that I've just put into that recovery cylinder afterwards, after I've pulled out that dye refrigerant, is now going to get contaminated with that dye, and that whole tank needs to be destroyed. All right. So I'm very hesitant about using dyes for that reason. It'll contaminate everything. So stick to maybe other types of methods, electronic leak detection. Same thing applies if you use those stop leak products. That goes into your recovery cylinder. It's going to contaminate your entire cylinder. All right. Or even for that matter of fact, a compressor burnout. If you have a burnout, that goes into a recovery cylinder. That'll contaminate all your refrigerant. Digital charging scales. So we need to know how much refrigerant we're putting into a system. The easiest way of doing that is to use a scale. The reason we use a scale is to know how much refrigerant we're putting in first off. All right, that's going to be critical because certain applications require a specific amount of refrigerant in that system. Those are critically charged systems. Let's just say we're talking about like a little walk-in cooler. Maybe it holds 2 pounds of refrigerant. Exactly. I need to be able to put 2 pounds of refrigerant in there. All right, I can't go off of just superheat or subcooling, and the reason being is there's going to be different conditions that it operates off of, and it may have just too broad of a range for that. And so I need to go off of what the manufacturer recommends, which is 2 pounds. Okay, great. Ductless systems are the same way. They're going to tell you how much refrigerant the system requires, and okay, it's going to operate in both heating and cooling mode, so you don't know which one, and so there's a lot of variability with it. So we're going to charge it based on what the manufacturer recommends. So we put our tank on the scale, we zero it out, and now we can add refrigerant into our system, and the scale is going to tell us exactly how much refrigerant we put in. The opposite's true if we're recovering it. All right, if we need to recover the refrigerant, we can weigh in how much refrigerant we recovered, and that way we can use it for documentation or for refilling the system. And that's it, gents. That's all of it for today.